Hi folks, welcome back to 5.1 part 2. So before we learned about what happens if we could find a nice formula for the area, and we were able to use what we know about geometry to help us find that area. And then we put on some new notation, so that integral symbol talking about where you start and you stop, whether it's going to be positive or negative area. Those are all things that we talked about in the first video. So in this second part, we're going to address this question right here of, but what if the curve does not produce a geometric shape? Meaning, what if it's not a perfect circle or a perfect triangle or a perfect trapezoid? And so we're going to start right here with this integral, the integral from 0 to 2 of x squared dx. And so what I'm going to do is I'm going to use the graph below to go ahead and draw x squared. Okay, so the function that I'm interested in is x squared. And I want to find the area between the x squared and the x-axis. I want to start at 0 and I want to end at 2, okay? So let's plot out some points for x squared. So if I take 0 for my x, here let's make a table, x, y. If I plug in 0 for x, I will get 0 for y, and I can plot that point right here. If I plug in 0.5 for x, 0.5 squared will give me 0.25 for y. So at 0.5, I'm going to end up somewhere here. At 1, when I plug in 1 for x, I'll get 1 for y, so that's going to be right here. When I plug in 1.5 for x, and I square that, I'm going to get 2.25, so 1.5, 2.25 is somewhere there. And when I take 2 and I square it, I'm going to get 4. So 2 and 4. Okay, so this is the graph for x squared. And if I go ahead and connect these, okay, I notice that the shape underneath here between this curve, remember we draw that perpendicular whenever we get to like an end point. When we get to this area underneath the curve, it's not a triangle, it's not a rectangle, it's not a circle, it's not a trapezoid. And so what we're going to do is we're going to practice approximating. So there's something, so we can approximate the area with something called LRAM. So let me highlight that. LRAM. Okay? Now LRAM means we're going to draw some rectangles. And how many rectangles are we going to draw? We're told by this number n equals 4. So I'm going to take this distance, which is 2 units, and I want to cut it into 4 equal pieces. So I cut it in half, and I cut each half in half, and now I have 4 equal pieces. So that represents n equals 4. And then what we're going to do is we're going to draw vertical lines from each of those until it touches the curve. So here, 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 and we already drew this one, but I'll go ahead and draw it again. Okay. Now I can kind of see that there are 1, 2, 3, 4 sections. And now what we're going to do is, because this is LRAM, that stands for left rectangular approximation. Okay, This left rectangular approximation, what that means is for every rectangle, I'm going to go to the left side of it, and I'm going to draw a horizontal line. So if I look at rectangle 4, the left side is this side. So I'm going to go up until it hits the curve, and then I'm going to go directly across, and I'm going to shade in that rectangle. Okay. Now let's go to the next one. So for the third rectangle, here's the dividers. The left divider's here. So I'm going to go up until I hit the curve, and then I'm going to go across, and this is my second rectangle. I'm going to do the same thing with the second one. So here's my second divider. I go up until I hit the curve, and then I'm going to go across, and I'm going to shade that rectangle. And when I try that for the first rectangle, it's at 0, so that's okay. It's just like a flat, not a rectangle, just a line. Okay, that happens sometimes. Okay, so what LRAM wants us to do is they want us to find the area of each rectangle and then add them all together. So, our rectangle, let's start with this first one. This first rectangle has a base of 1. Sorry, it does not have a base of 1. It has a base of 1/2. Okay, so 1/2. And then the height of that rectangle, we said this one was the flat line, is 0. Plus rectangle 2 has a base of 1/2. And it has a height, let's see, how high did I go there? That's that 0.25 plus 1/2 times the third rectangle, well, that went all the way to 1, plus 1/2 times this rectangle went all the way to 2.25, and that was it. We only had 4 rectangles. Now, before we add these all up together, I want us to simplify this a little bit. And so what I notice is that every term has a 1/2. So I could also say that 1/2 is the greatest common factor. So I'm going to go ahead and take that out to the front. And then let me think about where all of the other numbers came from. So, whoa. So 0, well, the y value of x0 was 0. And 0.25, well, that was the y value of 0.5. And 1 was the y value here. And 2.25 was the y value here. So of all of the y values that we had, we took the left ones. And so we could say that we say f of 0, because that was the left mark here, plus f of 1/2. Well, let's use 0.5. Let's stay constant. 0.5 plus f of 1 plus f of 1.5. And that's another way to write it. And let's just turn all of this to a number, see what we get. So we get 1/2 times 0.25 plus 1/2 times 1 plus 0.5 times 2.25. And we'll get a total area of 1.75. Okay. Now, if we look at our diagram, all of my rectangles, they leave a gap. Like I have like this space here that I didn't count, this space, and this tiny space here. So I'm going to go ahead and say that 1.75 is an underestimate. I knew I was estimating. I knew my answer wouldn't be totally correct, but I also know that it's an underestimate. And I think the easiest way to find that is to look at your diagram and see, do you have extra space or did you go over? Okay. So let's go ahead and try question 2. So question 2 looks kind of similar. It says approximate the area, but this time they're saying with RAM. And they also tell us they still want to cut it into 4 rectangles. But RAM, as you've probably already guessed, talks about the right rectangular approximation. Okay, so we're going to draw the same picture. 0, 0, 0.5 and 0.25, 1, 1, 1.5 and 2.25, 2 and 4. And I'm going to connect those. Whoa. Okay. And I'm going to divide it into 4 sections on the bottom that are all going to be equal. So n equals 4. And I'm going to draw my vertical lines at each of those. Okay. Now this time, instead of picking the right or the left endpoint, we're going to pick the right one. So if I start with rectangle number 4, and maybe let me do this in a gray. If I start with rectangle number 4, here's the left side, but here's the right side. So I go all the way up and I draw that rectangle. So I can already tell that because the bar is taller, this one is going to be an overestimate. Okay, let's do the rectangle number 3 is going to be here. Again, an overestimate. Rectangle 2 and rectangle 1 is not flat anymore, it's actually got an area. And so what I'm going to do is I'm going to say, let's use this part of the formula to help us figure out which things to use. So I know that all the rectangles have a base of 1/2. Now they all have different heights. So the first rectangle, I don't use f of 0, I use f of 0.5. And for the second rectangle, I use f of 1. And the third one, I use f of 1.5. And the last one, I use f of 2. And so I can actually just pull the values from my table, but this time I want to pull the bottom 4 y values. So I'm going to get 1/2 times 0.25 plus 1 plus 2.25 plus 4. And when I type that all in, I get a total of 3.75, which is way bigger than what I got for my left estimate. This one is an overestimate. Overestimate. Okay, so we're going to stop here for video 2. Come back and we will finish up this problem with 2 other ways of approximating. See you back here.